Okay, now here's the real question, right? If I'm going to look at this, when I take a volume, how do I know which method to use, right? That's the age-old question. I can find volume. I have two ways to find volume. The question is, which method do I use? I don't know. Let's take a look. Region R is bounded by these graphs where I have f of x is equal to 2x minus x squared and g of x equals x on the interval here from 0 to 1. I'm going to revolve about that x-axis. All right, let's draw these graphs. So it looks like I got a quadratic in a line here, and I'm bounded from 0 to 1, so I know it's going to have to be in that first quadrant. I'm going to come out here and make this a 1. And make that a 1, just because it looks like it's going to hit here nicely. So from 0 to 1, I know that this g of x equals x. I'm probably going to make that red here. That's just my line. Slope of 1, right? G of x equals x. Okay, now the question is, with my quadratic, I know it's going down because this is negative here. So let's see what this looks like. If I graph that quadratic, oh, we can graph that a couple different ways, can't we? Let's see what's going on. What do I want to go blue on it? Sure, why not? So I've got f of x is equal to a 2x minus x squared. If I find my vertex, I know that this is negative b over 2a. So I've got negative b, which is negative 2 over 2 times negative 1. That's going to be a 1. So f of 1 is equal to 2 times 1 minus 1 squared. So 2 minus 1, oops, is 1. So I have the vertex up here at 1, 1. Now, if I plug a 0 into this, 0 times 0 is 0. So I've got the point 0 and I've got the point 1, and I know that's my vertex. So if I were to graph this, it would go on down this way, right? Because it's the vertex, it's the highest it could possibly go. So here's my piece. Oops, let's actually color that in. Does that make sense? So I know my vertex here for this graph, this is going to go down, and it's going to, I don't know where it's going to hit over there. Oh, it's going to hit at 2, right? Because if I factor out an x, I've got 2 and 0. So those are going to be my intercepts. So this is my parabola that I'm looking at. But the only piece I'm concerned about is this one. Okay, where are we going around? The x-axis. Okay. So let's talk about this for a minute. We have two choices. I'm going around this x-axis. If I go around the x-axis and I'm using the disc washer method, that is the same. Washer disc method is the same. So I have a top and a bottom. So we could pull that off. This top is f of x or y is equal to 2x minus x squared. This is in terms of x. I have the x-axis, and this is in terms of x. Everything is the same. And we can pull that off here at the same. My interval is going to go from 0 to 1. All of that is the same. That's a good tip-off for the washer method. All right, if I can make everything the same, then that's what we want to do there. So my volume here, washer disc method, is going to be pi r squared. So I've got pi from 0 to 1. My radius here is going to be my top function minus the bottom function. Remember that? That washer disc method, we're taking it from the old one, the previous section, not the old section, the previous section into this one. So for that washer disc method, pi r squared, my radius is the top. So 2x minus x squared minus my bottom, which is just x squared dx. If you can make everything the same variable, that is your washer disc method. Now I'm going to scoot this up. Now we just integrate. So let's get this thing out of the way. Oh, that's just squared, so let's go ahead and just multiply this out. I'm going to go from 0 to 1, square the first term, minus, multiply those together by 2 for x cubed, and then square the last term, power to a power you multiply, and then minus an x squared dx. And then what do we have? We got a couple of like terms here. Oops. We do not have. Those are not my like terms. Tune in, Bradley. These are my like terms. I just underlined the wrong thing. 4x squared minus x squared. From 0 to 1, I now have 3x squared minus a 4x cubed plus x to the 4th dx. I'm not going to put those in descending order because I don't really have to. It's fine. Then we integrate. Add 1 to that will give me x cubed divided by 3. Divided by 3 is just a straight up x cubed. And then 4 divided by 4. Oh, well, how handy is that? X to the 4th plus a 1/5 x to the 5th. So I only have one fraction. That's cool. And I'm going from 0 to 1, so it's kind of my best day ever. So I've got pi will be 1 minus 1 plus a 1/5. And then, of course, minus 0, because it's what we have. 1 minus 1 cancels out. Da-dun-da-da. And I've got my volume is equal to pi over 5, or 1/5 pi. Same thing. Not bad, right? Now here's my question to you. What if I were to try to do the other method? I don't want to redraw this. Let's use the beauty of technology here. Oops, I'm going to come out and get that. So let's copy this. I'm going to paste it over here. Oh, technology is a wonderful thing. Isn't it though? What if we wanted to try the shell method? Let's talk about it for a second. What if we wanted to try the shell method? Okay. That means if I'm going around the x-axis, everything has to be in terms of y, because I'm going around the x-axis, right? So because it's the x-axis, everything has to be in terms of y. That means all my functions have to be in terms of y. Now for this one, y is equal to x. That one's gold. No problem there. But look at this function. What if I'm looking at this and I say, all right, y is equal to 2x minus x squared? That is going to be unpleasant. This is not an easy conversion to y. I would have to get x equals something there. And I've got two x's in there. That's not going to be a nice, easy conversion to y. Why are you going to put yourself through all of that? You're not going to, because that's why we have two methods. This one, disk washer, makes way more sense because I can't put everything in terms of y because of how this is set up. And it's already set up super nice and easy. Efficient math, right? Efficient math. So we want to make sure that we get ourselves set up with where we need to be. Okay, good, good. How do I look at this? Then that's going to be part of this assignment, making sure you know which method to use, what's the most efficient and the best way to approach these problems.